Welcome to the Flux, where we hear stories from people who've asked what-if questions to better understand the world and talk about how data can help tell stories that impact decisions and create an intentional impact on the future. This is your host, John Cordier, CEO at Epistemics. In a world where the flux capacitor from Back to the Future does not yet exist, people have to make difficult decisions without always knowing how the future will play out. Our guests are people who've taken risks, made decisions when uncertainty was high, and who have assisted decision makers by using data and models. We hope you can turn lessons from our podcast into foresight so you or your organization can make better decisions and create an intentional impact for others. Hey there, welcome to another episode of The Flux. Today we have Andrew Crooks joining us. Andrew, thanks for making the time to step out of the conference and pop onto the podcast.
I'm more than happy to be here. Thanks.
Cool. So we're here in Santa Fe. It's the Complex Social Systems Society conference, talking a lot of agent-based modeling, system dynamics. For people that are just tuning into this podcast for the first time, some people are very technical, some people are less technical. The audience of listeners ranges from some students all the way up to some governors and executive business decision makers. So to get started, Andrew, why don't you give us a little bit of a flavor of what got you into agent-based modeling and complex social systems in the first place?
Yeah, so many years ago now, back when I was doing my PhD in London, at University College London, I was sort of assigned to look at all this data. So I spent a year analysing data and so forth. But the data is only giving you the sort of the patterns, right? So it gives you sort of the, average household income or mean travel distance and things like that. It didn't tell us why that data exists or how that data emerged from lots of individuals, right? And at that point, agent-based modeling was relatively new in the UK at the time. And my advisor is like, well, why don't you try doing an agent-based model of residential location? And well, it all started from there, really.
Okay.
And then, so that was back in 2003. And then since then, I've just been developing and exploring various types of agent-based modeling applications with a specific focus on geographic information systems. So I try to make a lot of my models linked to actual real-world places.
Sure.
To understand really what's happening around us.
Cool. So some people who might be new to agent-based modeling, is there a story, a metaphor, something that you've found is an easy way for people to approach agent-based modeling if they're new to it?
That's a good question. So often when I'm teaching agent-based modeling, I try to get the students interested in agent-based models, and I have analogies from there's a company called Massive who do all the large crowd simulations and so forth, like Lord of the Rings, and I show them images from the fight scenes or the migration scenes from various movies.
So just like the orcs are just running on screen, just having a okay, cool.
And and I say, well, of course we are social scientists, so we have to then make them a bit more simple than that. And then the idea with models is that we can test ideas and hypotheses that we can't do in reality.
Sure.
So a lot of and one of that example would be, I can't set a building on fire. Well, I could set a building on fire, but I'd go to jail, right? But if I want to simulate or explore how people might react to a fire and where they might go, I can build a model and explore those types of things. Or another example is the traffic.
Okay.
Especially in America, one gets stuck in traffic all the time, right?
Sure. And we haven't totally figured out, how to move people around all that well.
Well, Buffalo's very good because for that. There's not many traffic jams. That's for a different reason. But agent-based models, one of the main application areas is in traffic simulation. But also, it's a good example of emergence phenomena. So, there's a very simple model of explaining a shockwave traffic jam. So when you're driving along the road, you hit a traffic jam, and there's no accident. It's just because people can't drive at a constant speed and they get distracted on things. So give some people in the model some simple rules. If there's a car ahead of you, slow down. If there's no car ahead of you, speed up. Those two simple rules lead to sort of traffic jams emerging. But of course you can make them more complicated. And then I can show them a real life experiment where some Japanese researchers got 30 odd cars to drive around in a circle, and the same shockwave traffic jam emerges, right?
It's like it was like everybody had to drive 30 miles an hour on this same track And even with that rule, you end up getting traffic jams.
Exactly.
Yeah.
So I give them like those types of things I try to explain, and the idea is individuals lead to more macro patterns emerging. So I hope I answered your question there.
Yeah, absolutely. So one of the things that like your work does is try to really get the geographic representations very accurate.
Yeah.
What have been some of the challenges, or how has that evolved over the last 10 years of what was possible to now what is possible?
Yeah, no. So even going back to when I started my PhD, in the old days, you couldn't. So in GIS, there's two types of data structures, broadly speaking. There's raster and vector. Raster is your imagery data. Vector is your points, lines, and polygons. When we first started doing this type of work, none of the agent-based modeling toolkits at the time would have been Repast, Star Logo, Net Logo, Swarm. None of them could really link vector and raster together. So it's only since like Mason and like 2010 timeframe that people could to do that. So one evolution is the ability to add the raster and vector, and that's important because a lot of data, remote sensing data, if you're on land cover or land use, that's like a raster data set because it's coming from the satellites. But then if you want population data, that's coming from census data, which is polygons.
Yep.
So overlaying those types of things wasn't possible until more recently. Now it's sort of mainstream, and nearly all the toolkits can have raster and vector on top of each other. So that was one of the challenges. The second I would say was computational. It's amazing how powerful machines have got over time. So recently, like last year, I reran what I did for my PhD, which is quite embarrassing now. And what would take a week to run during my PhD on a standard PC at the time can now be done in like 10 minutes.
Okay.
Right. So
wow.
there's that. So computational power on individual machines has changed, and the toolkits has changed, the availability of data has changed. Because in the old days we had more traditional data, like slow data, like census data and things like that. Now you have more high frequency data that you can play around with to get better ideas, like the social media data. That has and a lot of that has a geographical component that we can look at, and then. I think those are like the things that strike me as really has changed a lot.
Sure.
And then what's really quite interesting is when we first started doing this, there wasn't that many examples out there, models. So something that we've been promoting over the years is giving example models out.
Absolutely.
So people can learn from them. And now there's a whole plethora of GIS and agent-based models out there. That's coming out. And then another thing I think is quite interesting is the growth of synthetic populations.
Sure.
Because like for initialization of these models, and in our group, like in many others, we spend a lot of time creating these synthetic populations, and now we're trying to create frameworks and things like that to create the individual agents and then apply them to different case studies. And that's saving us a lot of time.
Right.
So we can now just like plug and play that into our models.
Right. So there's something that you mentioned that I want to go back to. Never asked this question before to anyone, but taking a week to run the model, now today taking 10 minutes.
Yeah.
How do you think that's going to impact like true innovation and the ability to like understand what's going into these models, like based on the time span that you're waiting to get results back, but also like you can spin up a bunch of stuff really cheaply now?
Yeah.
Like what do you see like amongst students that's changed?
So the running of models, like now students say it takes a long time to run the model, and their definition of long time is 10 minutes.
Right.
And I'm like, that's not. So it's really interesting, their definition of how long is long, but to get that result more quickly, they get more feedback, and then for them it's helpful for redefining the model or like tuning the model or altering these things, because you're getting the results much more quickly in that. But also what I see in the students these days is the changing in the approach that they come to the modeling. So in the past, we had two types of modelers. We had the more computer science side that were heavy into Java. That's how sort of I started in here. And then you had the more social scientists that were using sort of Net Logo. But over that, and when we were when I was teaching this agent-based modeling at George Mason, nearly everyone was using Java at the time. But then there's a sort of phase shift, so to speak, right? Around 2015, when people started using Python a lot more.
Right.
So, and that change in people programming Python now is changing, I think, how people are trying to create these models as well. And that's giving a lot of new opportunities as well, because now you can, in the old days, if you wanted to analyze your model results, you wouldn't use Java for, you would have to use either a statistical package, R, or something like that. Now with Python, you can have the whole ecosystem in one language, and students can easily more adapt to that, and they're not complaining so much about learning, having different languages for different aspects of the modeling in those types of things.
Yeah, makes sense. So for some of these agent-based modeling and geospatial use cases, is there a field that you feel like is more willing to adopt agent-based modeling connected to GIS?
It's funny because I laugh because I'm a geographer,
Yeah.
so I'm like, geographers like these types of GIS ABMs, right? So it has a long history, and not just agent-based models per se, but also like going back into the 1990s cellular automata models, right, which is sort of a precursor to agent-based models. And they've been heavy users of spatial data, especially remote sensing data. And so anything that has like a diffusion process, you can sort of capture those types of models really well in that. And then people interested in sort of urban growth, residential dynamics, pedestrian modeling, where that spatial element is crucial for understanding how people are going to navigate through the streets or the subway stations and things like that. And then traffic simulation, again, anything that has like a sort of a spatial component, and you need to know the distance between one place and another place, or the width of the road if you're doing really detailed traffic simulation models, and things like that. I think they're really quite those are the ones that need really liking the sort of GIS type of stuff.
Sure. So sometimes this question comes up. People like to use agent-based modeling because you can run what-if scenarios without having to light a building on fire or whatever else and see how that plays out. Like when you look at the future of where synthetic populations are going to be going, is it that the agents are all the more reflective of us as people, or is it that the agents are interacting in basically like your Google map is coming to life? So the workplaces have names and they're connected to these industries and they're connected by firms that are making decisions. Like how do you see the evolution of synthetic populations changing over time?
So, going back to like the traditional synthetic populations that Orkut was trying to propose, right? He just wanted individuals that were heterogeneous, right? And I think we have that heterogeneity in the synthetic populations now. Some synthetic populations are better than others, of course. Like the ones I create, we have households, but we don't have very good structures like twins in household structures, or and some of the or the different types of couples. But I think the synthetic populations are getting richer with respect to the sort of households that we see today, which weren't really captured traditionally.
And about the social structure in the household, not necessarily like this is a home with that was built in 1970 and has this for its roof and here's its square footage. Like,
so when I say household structure, I was thinking maybe like you have two parents or two same-sex parents or one single parent, the kids in their structures, and then linked to sort of social demographic information. So like income could be high, low, medium, depending on how one collects it. So different countries collect different types of social demographic data, and if people are mixing all those, so you're getting a richer population, and then you can utilize that in your model. So one of the projects we do at the moment, we are looking at synthetic individuals. We have income, and then jobs associated with their income, and then we assign them to buildings that match sort of their income. So rich people live in rich expensive houses, poor people live in poor houses, and then rich people will work maybe in offices, poor people might be working in more less skilled activities.
Sure.
Of course, that's going to impact their work hours. So through those types of rules, we can then build activity patterns of how people might move through the system.
Right.
So I think there's that side. We're getting much better at creating synthetic populations. There's also the networks, so the household network, and then, for example, with household network, you have to then do things like I'm blanking on the term, where coordinated movement, right?
Sure.
So if you have one of the areas that you don't see very often in the models is, if you have two parents, which parent's going to drop the kid off at school?
Sure.
Right? And we know where the schools are, of course, because of data like OpenStreetMap or data collected by the Department of Education and things like that. So you can build those types of things, and then networks in general, your friendship networks. Synthetic populations have come a long way from just individuals. Now,
right.
I see people get connected together on social networks, their home networks, their work networks, their just club networks. Not so much with soccer clubs and things like that yet, but so that's important, because like for certain applications like disease spread,
right.
you need to know if the kid's at school, he gets exposed to sort of a COVID or whatever, comes home, impacts mum, dad, and then he has a brother. The kid's in elementary school, the brother's in high school, then the brother goes to high school, infects the kids at high school, and then it just propagates through the system.
Yep.
And you sort of saw those people have started playing around, exploring these things, but they haven't come mainstream yet, I don't think. Or maybe they have, and I just don't know about it.
I mean, yeah, we see the social contact network, household, schools, workplaces, where people are, how much time they're spending in each of those places. That's kind of becoming like the standard baseline.
Yeah.
And then enables people to think about, like, well, what is it that we're actually trying to solve for on top of that baseline? But as it comes to networks, even seeing things like adding, like who's on what social media platform and who are they connected to?
Yeah.
Who gets their news media from Fox versus CNBC versus CNN, and how does that impact the information networks that how information spreads across the country? Have you seen ways that people have been able to add that into the synthetic population that doesn't totally blow up the compute?
So that's what you asked. The previous question you asked about, like, other things about synthetic population, and data is one of the interesting things now, like social influence and things like that. So we started playing around with. When I say playing around, I should really say researching, right? But it's
taking it very seriously.
But that's the nice thing about this type of work. It is exploration, it's experimentation. So going back to the influence of social media channels or whatever on people's opinions, we've been trying to do that with respect to vaccination uptake.
Okay.
So, for example, in New York State, we have lots of data on how many people got vaccinated and when they got vaccinated.
Right.
But we know vaccination is a highly charged political issue. You have the anti-vaccine, the pro-vaccine. You can analyze social media data through like natural language processing techniques to sort of get pro-anti stance. But that's one thing. But why do people get vaccinated, right?
Right.
So you've got that notion of social influence, but what is your social influence? Is it that cyber influence, your Fox News versus CNN, I guess? That's why I'm still getting used to the American channels. Or is it, your social your peer network, your
right.
Right?
Who are the 20 people that something goes wrong I might call?
Exactly.
Yeah.
So so now we're exploring how those types of how you have your social influence on your peer network versus online, and of course people weight that differently, and through agent-based models you can explore those ratios, like, do I trust my wife more than my colleagues, or do I trust what I'm reading online more than my social group? And we started explore. Our first case study for this was a small county just south of Buffalo that was 50% rural, 50% urban, and we thought that was quite an interesting county because through that, it sort of mimics part of middle of America, I would say.
Right.
And we could get the model to the timeline of vaccinations we could mimic roughly what we could see playing around with weights.
Okay.
Of like influence. So in the first, that example, after tuning the model, so we had free networks. We had our kinship network, your family network, your relational network would be the people that you interact with on a daily basis. Again, all this is coming from your synthetic population.
Right.
Then your social media network.
Yeah.
And that social media, and for this county, people. It appeared by playing around with the networks that people were more interested in the family network, kinship, and the people that they interact with.
Okay.
But then we were like, okay, we got it for one county. Let's explore it for the whole of New York State.
Okay.
And so we created a model, and then but the rules for that, the outcome for New York State was not the same weighting scheme for that one rural county or middle 50-50 county.
Sure.
So and then like in New York City, this appeared through the dynamics that people around New York City were more influenced to get the same vaccination trends that the data was showing us. They were more interested in online.
Sure.
On things like that, and they vary across the state.
Right.
But I think you can explore those types of those things through social networks in these synthetic populations, and then work out what's happening and why it's not happening.
Sure, and then you kind of explore different types of networks where, in a city, sometimes it might be more advantageous to have more friends rather than spending more time in your family for economic reasons.
Yeah.
And that, it's something that might influence, information dynamics more so in New York City versus somewhere 60 miles outside of Buffalo, where it's kind of like farmland still.
Yes.
Yeah.
And so the variation, and I never thought I would explore this type of opinion, these networks, but now we have the ability to do that, right? Which was not really there 10, 20 years ago. And I think and networks are important because those are the things that influence us.
Right.
And we can capture that in these new synthetic populations. But also it adds baggage. So earlier we said, models now are relatively quick to run. But when we were modeling the New York State one, granted we didn't do any network optimization, but to run the New York State, which is like 20 odd million people, and their social networks, and then how information passes through that social network, is on a relatively powerful server. It's taking us about 22 hours to run one iteration of the model.
Sure.
Right. And yes, we could probably speed it up if we had more. Maybe we went onto the cloud, but there's still really some big bottlenecks on large-scale simulation, at least from our point of view. Because
we've seen it too. Like even running on I'm not going to call out any one of the three major cloud providers, but like even on their largest instances, sometimes it doesn't even enable one simulation to complete a run. Yeah. But we'll work on that.
And it's that notion. So in a previous life, I was working on an agent-based modeling platform on Mason. And we would trying to do distributed Mason, so basically run the model on multiple nodes. And it works really well for models that aren't very spatial.
Sure.
Right? Or there's not much movement between the nodes. But when you start adding the GIS, the networks, and there's information passing between the nodes, you don't get much speed up.
Right.
So I think one of the big challenges from the ABM community, from the running large scale models where agents are moving around a lot, is trying to understand how you can get that speed up without simplifying the model, which is what we often do, is simplify the model to get rid, so we don't have so much messaging passing between different nodes and things like that.
All right, I think we have time for maybe 2 or 3 more questions. One of the things that I like to ask everybody who's on the podcast is what the Flux moment for you? And by that, the podcast is called The Flux, named after the Flux capacitor from the movie Back to the Future. If you could rewind in time and say, all right, at this moment in world history, if we were able to run some simulations to see how this decision was actually going to play out with some high probability, what decision might you go back to try to, influence future course of the world?
That's a really good one. So I will. No, oh. Yeah, I'm thinking. Okay, so one thing that has caused issues in my family is Brexit.
Okay.
Right. So maybe it would have been nice to have a model or exploration of, how might people vote during those types of events, and how that might have changed the course of action, and also therefore the larger ramifications of the unforeseen consequences of Brexit during the time frame. So that's just something I think. Yeah, that's like, very short term, very personal type of thing.
Because that decision, it has a cascading impact.
Yeah,
and like seeing how that impacts seemingly family dynamics is one.
Yes,
there's economy dynamics, trade dynamics, like all those things from a decision.
And it's also like that. One of the challenges of models is that we can't model everything. So it'd be really interesting to see if we can model all those various aspects and pull them all together as well. Yeah.
Mm-hmm. Yeah, absolutely. So to kind of wrap up, there are two questions that we wanted to end on. First, what excites you about where agent-based modeling is going? Brighter future for the whole field. And then the follow-on to that is, how does somebody take the first step to start getting involved with agent-based modeling if they haven't already?
Yeah. So what excites me at the moment, and it's going to sound terrible because everyone talks about AI. But I think the ChatGPT and those types of things are really, really exciting, because from what I've seen so far, you can upload a paper, and ChatGPT can summarize the paper, tells you what's important. If I want to create a model of X, I can ask ChatGPT, read these papers, summarize these papers, identify what's important in these papers, and you can do that. You can spit out the answer, but then you can take the next step and say, look, can you create me a model in Python, NetLogo, and ChatGPT will create a model for you.
Right.
And a lot of people will say, well, you can't trust what ChatGPT gives you, but what I think is really interesting there is how. Yes, it might not be perfect, but sometimes we create models that aren't perfect ourselves. The issue of bringing in bugs and things like that. But it lowers the boundary, entry level. So, in the old days, you had to be good at programming to create agent-based models. Now, with these language models, one doesn't necessarily have to know a lot about programming. Some programming, yes, but, ChatGPT can help you on those elements as well. So I think, what excites me is what you can do with the AI now, these large language models, and how it's lowering the boundary. And if you lower the boundary, you'll get people interested.
Right.
And if you can get people interested, that's sort of gets us to the first steps of what's coming next. And you just need people to play around with models. Right. So there's a lot of now ways, like a lot of the toolkits, you can spit out the models and put them in web browsers. So they're very simple models, right? Like Meta. Or run NetLogo models on the web. Just getting people to play around with models and understanding what that's for us. One of our introductions is getting recently I was getting my students just to play around with some NetLogo models online to see if they get interested, and then from that, to start building the models themselves.
Right.
But with the AI, ChatGPT and things like that building level has come down a lot, and it's not just simple models you can build with these things. You can build geographically explicit models with them as well. Right. So we were doing a model recently on restaurant choice because we were curious about restaurant choice, and so ChatGPT we said read the paper, and ChatGPT read the paper, identify the main elements that are important to go to a restaurant, so cost, quality of service, food, things like that. And then we asked them, okay, parameterize this model based on some Yelp data on restaurant locations and reviews based in St. Louis, because I don't know why we chose St. Louis. We chose because it has a diversity of restaurants, and also it wasn't Buffalo. Okay. And but ChatGPT created us.
People wanted to look for more than just buffalo wings.
Yeah, exactly. Yeah, and ChatGPT created us that geographically explicit model, and I was like, wow, that took half an hour or so. Well, half an hour to get the basic stuff running, and then a lot more prompting to get but it still didn't have to do much coding. Sure. And that's just for me amazing. Yeah. So that's something that excites me, and also I think that's going to help bring people into agent-based models.
Awesome. Well, Andrew, thank you so much for spending the time outside of the conference to be on the podcast. Yeah, it's really exciting stuff.
Thank you.